chemistry. Martin and I are doing module 14 practice problems. Number 1.
Milk sours because of a chemical reaction that takes place between some of the chemicals that make up the milk. Why does a carton of milk left out on a countertop sour sooner than a carton of milk left in the refrigerator?
This has to do with the principles of reaction rates. And what do we need to know?
They're faster when the temperature is higher.
Right, so increased temperature, increased reaction rate. So it's obviously, unless it's really, really cold, then it's going to be warmer on your countertop than it is in the refrigerator. Okay?
A chemist, 2. A chemist does a reaction rate analysis on the following reaction. 2NO gas plus O2 gas yields 2NO2 gas. She collects the following data. It's on page 489 in the first table. What is the rate equation for this reaction?
Okay, so the general rate equation is R equals some K constant times the concentration substance A to some power X times the concentration of substance B to some power Y. Okay. So what we need to do is we need to look at the actual data, okay, in order to figure all this out. So let's look at the nitrous oxide. Okay. What is the NO? What happens to the concentration between trials 1 and 2?
It doubles.
What happens to the instantaneous reaction rate?
It halves.
How about between 1 and 3?
Between 1 and 3?
Yeah, where it's
the
same concentration.
Oh, then it doubles, I think.
Yeah.
Yeah, that doubles.
Okay, let's look at the concentration of the oxygen, the first one and the second one. Did they change at all?
No.
No. But the concentration in trial 2 changed of the NO. What happened to it? It doubled.
It doubled.
And then the reaction rate halved.
Yeah.
Okay. So what does this tell us about our values for X and Y? Anything?
Sure. The value for
Don't look here.
Is
thank you.
0.012.
No, the value for X. How do we calculate the X?
2.
Why?
No, 2x. Because
hold on. We're making a mistake. That's not halved. Look at it.
Yeah, I was thinking about that, but
Sorry, I'm not wearing my reading glasses. I'm having trouble reading this book. Should probably go change my glasses. The concentration did what? It went up how many times?
It decreased.
No, it didn't decrease.
It increased.
Look, this is 0/10,
yeah.
and that's 1/10. This is 2/100, and that's 11/100. So what happened to it?
It increased.
By a factor of what?
I don't know.
What's the first instantaneous reaction rate? 0.0281. 0.0281. What happens if we double it? We get 0.0562. What happens if we double that? We get 1124. So that's close. This is 4 times what happened, okay? When the concentration of NO doubled, the reaction rate increased by a factor of 4. Okay?
Yeah.
So that means that x is 2 because we're going to get a fourfold increase by doubling the concentration. The only way we're going to get that is by squaring the concentration, right? Double the concentration, you got to square it. You got a fourfold increase. Okay. Look at the value of y in trials 1 and 3. When the concentration of NO is the same, what happens to the concentration of oxygen?
It doubles.
And what happens to the rate?
It
also doubles. Yeah. Okay? So that means that y equals 1, right?
Yeah.
All right. So now we can write out our equation with the correct thing. So the instantaneous rate is going to be K, we haven't yet determined, times NO to the square power times O2 concentration to the, what did you say, the 1 power, right?
Yeah.
Okay, so what is the concentration? So let's pick one of the trials. So we know the R, we know the concentration of the two substances. Let's use trial 1. What is R? It's 0.02, what is it?
0.125.
No, the first trial,
0.253.
No, the first trial. Read it to me. The R. I'm looking for R in the first trial.
0.0281.
0.0281.
Yes.
Molarity per second equals K times what's the concentration of NO? In the first trial.
0.0125.
Molarity.
Molarity, right.
And this is squared. And what's the concentration of the oxygen?
0.0253.
And this is molarity, and it's to the 1.
Yeah.
So. K is going to equal the rate constant, 0.0281 molarity per second, divided by 0.0125 molarity squared times 0.0253 molarity, right? So these things are going to cancel out. So we take open parentheses, 0.0128, close parentheses, divided by open parentheses, 0.0125 squared, close parentheses, times 0.0253, close parentheses. So how many significant digits do I want to have?
3. No, 2.
Where did I mess up? Oh, somehow I lost my 1. Whoops. Okay, slightly different. Let me try that again. 0.0281 divided by 125 squared times 0.0253. Let's try it again. Oops, syntax error. No, it wasn't. 0.0281 divided by, open parentheses, 0.0125 squared, close parentheses, times 0.0253 equals. All right.
What does it mean with the syntax error?
It means you entered something wrong and we can't perform that calculation. Oh. You entered an invalid term for us to figure this out by. Okay, so how many significant digits do I want?
3.
3. Okay. So here I have 4,
But
so I
that's
have to round
7,
to the
1,
nearest 10. 7, 1, 1. Or 7.11 times 10 to the third. And what is the units of K? We have molarity squared per second, right?
Yeah.
Okay. Oops, no, it's not. That's not bad. That's bad math. It's still in
Bad juju.
seconds times morality squared under 1. Okay. So now we are going to go back and we're going to calculate. Oh, no, that's it. So R equals 7.11 times 10 to the third, 1 per molarity squared times second, times the concentration of NO squared times the concentration of O2. Okay?
Yeah.
All right, and that's it for number 2.